In order to talk about differentials today, what we're going to do is to start back, all the way back into college algebra, maybe even before that, the first time that you saw the slopes and you first started calculating slopes and you calculated them for straight lines. And you would have m is equal to y2 minus y1 over x2 minus x1. And some of you may have seen a notation system that looked, trying to make like a little triangle, delta y over delta x. I'm trying really hard to make that look like a nice triangle. It probably won't look that nice all the time. All right, so the little triangle like this is the symbol for delta, and delta stands for the difference. Okay, so it'd be the difference in the y's over the difference in the x's. It's not normally that big of a triangle. It's usually something like delta y over delta x, but I was trying really hard. Okay, now, so and those of you who've seen other videos might know that writing neatly is a big challenge. So let's talk about that for just a second. What we did with that was to say this is the rise over the run. And we would do things like, let's say you had y is equal to 3x plus 2. So you knew, let's make that 4/3 so it's a fraction. As soon as my computer screen catches up to 4/3. Because we knew from that y is equal to mx plus b form that b is 2, and that would be the y-intercept. And the slope is 4/3. So we would start off with the y-intercept and we would go 0 in the x direction and 2 up. And then we would just count it off where we had 4/3 was the rise over the run. So we would run 3, 1, 2, 3, rise 4, 1, 2, 3, 4. Okay, and then we would go run 3 from that, 1, 2, 3, rise 4, 1, 2, 3, 4. And we would draw a little straight line. We didn't really care necessarily what those points were, where they were located. We just counted over the slope and drew a line. But let's go back over here for just a minute, and I just kind of want to ease you into this. So we started at the point 0, 2, right? And we had the rise over the run was 4/3. So what we would be actually doing if we wanted to know the points is we would take 0 and we would run 3 and we would take 2 and we would rise 4. So this would be 3, 6. And if you look at this graph, it looks like it's 3, 6. This one right here. Okay. Then we would take the 3, 6 and we would run 3 and rise 4 and we would get 6, 10. All right. Now, what I'm trying to get you to kind of think about is we knew the slope was 4/3. We know it's the rise over the run. So we could think of it as m is equal to the change in the y's over the change in the x's, which is kind of where we started, right? But we could perform this math, okay? And what we would have is, starting with m is equal to delta y over delta x, we would have m times delta x is equal to delta y. Okay, for instance, if our slope was 4/3 and our change in our x is 3, then our change in our y is 4. That's sort of like an infinite loop, right? And you're probably wondering, and what has this got to do with differentials? Why do we care? All right, so we care because of what's coming next. So I just want you to know that what I'm getting ready to come and do next is related back to this, okay? And specifically it's related to this. All right. So keep in mind that when we first learned about slopes, we learned about them for what's considered kind of like gross distances as opposed to little minuscule distances. So here was 3 and 4 versus when we were doing f of x plus h minus f of x as h goes to 0. Remember this limit where h is getting tinier and tinier and tinier so that this h is just right here, just little bitty tiny, where we would have instantaneous slopes and instantaneous change. So we have a line, right? The slope's the same all the way through, but a curve is not, that's not true, right? If you have some sort of parabola or, um, I don't know, some sort of, any sort of function that we've been working with derivatives, they're not normally straight lines. So what we would have then is, remember, your slope is replaced by your derivative, right? Because that's an instantaneous slope. So we would have, let me do something so it's red. We would have f prime of x is dy dx, right? This is still your rise. This is still your run. But instead of using delta y and delta x, which convey like distinct differences, like 1, 2, or 3, or 4 apart, units apart, this dy and dx is trying to convey to you that it's this infinitesimal little tiny distance, okay, so that it's an instantaneous distance. I mean, it's a limit. It's a limit distance. But it's following the same form, right? So we can say f prime of x dx is dy. Now I want to write the other one right underneath it. So we had m delta x is equal to delta y. And about here, you were kind of going, and why do we need to know that? Okay. And here is usually where your book starts off. Okay. So this is the differential. Okay. So just like before, when you had an equation like y is equal to 4/3 x plus 2, x was the independent variable because you could pick it. You said, well, what if x is 3? What if it's 1? So, and then y depended on what you picked for x. So it was dependent. Okay. Then what happens down here is that dx is independent and dy is dependent. So to get it into that kind of general shape that we're used to with the y equals, it would more often be seen dy is f prime of x dx. Okay? Now, can you also see that this is of the form y minus y1 is equal to the slope times x minus x1, because this is where we got our slope from. So remember, this is the tangent equation. This is the linearization, right? And so this is called the differential. Sometimes it's called this. The differential linear approximation. So really and truly, it's really and truly almost the same thing. They just use different words, okay? Different words for the title, different words for the bits and pieces. But if you're kind of going, man, it looks just like what I did last time, you're exactly right. Okay. So sometimes students get really hung up on that. Sometimes I get hung up on that, where I'm going, I'm not I'm not really seeing the difference, so I must not be picking up on whatever I'm supposed to be picking up on because they kind of all look the same. And if you're feeling like that, then yeah, they kind of all act the same. Okay. So the words that they use to describe them are different, and I think the considerations of what you can do with them are definitely different as far as applications. Okay, so let's move on and see what's going on. So this differential right here relates not gross or grand changes in x, not for a line where you're going to run 6 and rise 7. This is talking about really small changes in y and x, so keep that thought in mind. And so let's start a problem and say, let's say you have some function cosine x, okay? And they want you to find the differential. Now, you're going to need the derivative, and the derivative of cosine is minus sine x. And then what they want you to do is to say dy is equal to minus sine x dx. And that was always really hard for me to kind of keep up with. I don't know why I had a thing against that. I just did. All right. So what I do and what I encourage students to do is to think of it this way. Isn't f prime really dy dx? Because, well, in this case, it's dy dx because this is y and you have x over here. So this would be the derivative of y with respect to x. Okay. And this is minus sine x. Aren't those the same things? So then you know how earlier, we took delta x and multiplied it by both sides. So you can just think about doing that, and this is what you get. So I prefer to do it in terms of this with the dy dx, and then just move the dx over to the other side. And that helped me keep up with it. All right. Now, what happens if they want you to find the differential, all right, for an occurrence when x is equal to pi over 6 and dx is equal to 0.008. All right, so what you would say is the differential is minus sine of pi over 6 times 0.008. All right, and this would be minus a half times 0.008, which is minus 0.004, and this is the differential. So if they want it evaluated at x is equal to pi over 6 and dx is equal to 0.008, that's what you would give them. Otherwise, if they just want you to find a differential, kind of a generic one, that would be it up there. All right. So what if we have f of x is equal to 1 minus x squared over 1 plus x squared, and they don't want just the general formula, they want you to find the differential for x is equal to 2 and dx is equal to 0.005. Now, if they don't give you this information over here and they just want you to find the generic differential, we're going to go through that step in order to substitute this in. And now I'm going to take the derivative of f, which is y, with respect to x. So I'm going to write dy dx. And this is supposed to be a square. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. I was talking to a student today, and he went to A&M, and he said that the way they do it is it's low d high minus, I have to translate, high d low, and you draw a bar, and it's low squared. He had a little rhyme to it. All right. If that's what you've been saying, that's fine. Okay. Now, but I thought I'd share, just in case y'all have been saying that and frustrated, I validate the fact that that actually works. So when you clean this up, you get minus 2x cubed minus 2x plus 2x cubed over 1 plus x squared squared. So after a little bit more cleanup, you get minus 4x over 1 plus x squared squared. Okay, no big surprise for the derivative. And the differential is this. Multiplying both sides by dx. Now, you don't actually use this a whole lot in Calc 1. You come back around to it depending on how your book breaks it up, probably in Calc 3 when you're doing integrals of it. All right. Now, so this would be minus, okay, go back up in here, right? So if they just want the differential, this would be what you would be looking at, this part right here, right? If they want it evaluated at x is equal to 2 and dx is equal to 0.005. I think I had 2 zeros up there. Right. Then you would have minus 4 times 2 over 1 plus 2 squared times 0.005. So it turns out, after you reduce it down a little bit, it's minus 1 over 625. Now, you may be going, I'm not even sure what this means. Okay, so let's do an example where maybe it'll make that a little bit more clear. And let's consider a sphere. Okay, and it's got a circumference of 84 centimeters. I got this from an old book. It's like, I don't know, 10 years old, something like that. Stuart, it was a really good question. I just always liked it. Um, and so I thought I'd show this to you. So they have a sphere, and it has a circumference of 84 centimeters. Well, maybe. Okay, they could be off maybe with a possible error of 0.5 centimeters. I mean, I guess it's kind of hard to go around a sphere with a tape measure or something. I'm sure they could do it other ways, but you know what I'm trying to say. All right, so you have a sphere. Somebody measured the circumference. They think it's 84 centimeters. They could be off by as much as 0.5. Okay? All right. So the question says, let's say that they could possibly have a little bit of error. I mean, human error. What do you, I mean? So let's use differentials to estimate the maximum error in calculating another number, this time the surface area. Okay, so let's say you measure the circumference. You feel pretty certain it's 84 centimeters, and you might be off just, not much, but a little bit. But what about if we really wanted the surface area? I mean, how much is your little bit that you might be off? Okay, what's that going to do to the surface area? So you go out and you measure the sphere's circumference. You think it's 84 centimeters. You're pretty sure it's 84 centimeters, but it could be off a little bit, maybe about 0.5 centimeters. So you come back with a measurement, and I'm going to compute the surface area. Maybe I have to cover the sphere with some sort of really expensive substance. So I need to know what the surface area is. Pretty tight tolerance because it's very expensive. So we're going to do a little calculation. And the surface area is 4 pi r squared. And we know that the circumference, interestingly enough, for a sphere is the same thing as the circumference for a circle. So we have the circumference for a circle is 2 pi r. We know that the circumference is 84 centimeters. And we know that the error that could be, just because of maybe what you were measuring with was a little twitchy, a little bit off, you weren't really sure, that there could be a 0.5 centimeter error in your measurement. Now, this error is not an error in measuring the radius. It's this error right here, and it refers to the circumference. So I'm trying to compute the area based on the circumference, not r. All right. So I need to get from r to the circumference back to the surface area. So r here is the circumference over 2 pi. And I can substitute that in over here. And let's just call it a. The a is 4 pi. R is the circumference over 2 pi squared. Okay. Now, when you clean that up just a little bit, you would have the area, after you clean it up and reduce it, is 1 over pi c squared. So now I have the area in terms of c. So when I take the derivative to get a differential, I'm going to take the derivative of a with respect to c, because of a on the left, c on the right. And so we treat c, this is not implicit, okay, because I'm taking the derivative of c with respect to c. So I would have 1 over pi, and then you would bring the 2 down, leave the c alone, and take 1 off the power, right? So you actually have the derivative of a with respect to c is 2 over pi c. All right. Now they're wanting to know what the maximum error perhaps is. If there could be a potential error in the calculation of c. So if c is off by 0.5, let me put the dc over here first. Okay, so this is dc. So then remember, c is 84. And the possible error was 0.5. So I'd have the possible error in the area calculation, right, would be 2 over pi, 84 centimeters times 0.5 centimeters. So this turns out to be 84 over pi square centimeters. Now, depending on how they want you to answer that, this is the exact error. For us human beings who are like, I'm not sure what that means, this is 26.738 square centimeters. And you could round it off to your appropriate place. And for the relative area error, and this is the maximum error. I can say that word. This is the maximum error based on being off by the biggest amount you think you might be off by. All right. So the relative error is the computed one based on your possible error compared to the actual what it's supposed to be. Okay. So what this would be, turns out to be, is c squared over pi, that's what we had calculated, over this 84 squared over pi, because this is the actual area. And so this would be the centimeters. Let me put the numbers in here. 84 centimeters squared over pi. 84 squared over pi centimeters squared. So this turns out to be 1 over 84. This is the relative error. And if you want it as a percentage and divide that out, it becomes 0.012. or a 1.2% error. Okay, so what that means is if you're as much as 0.5 centimeters off of your measurement of the circumference, I could be as much as 1% off, 1.2% off compared to what the actual area is supposed to be. So I could be having to buy as potentially 1.2% more than what I anticipated based on this straight calculation according to math before I manufactured it. So I hope this helps just a little bit for you to see that a really good fit for these differentials is calculating up, this was my plan, this was my design mathematically, but then, sometimes when you manufacture things, you have an allowable tolerance, like plus or minus 0.1 or plus or minus 0.05. And how much does that throw off, what your actual intention was? What's the percent error? So I hope this helps explain it a little bit. Don't forget that the links to problems and to the next videos are down below. Please don't forget to like us and subscribe us. And I'll see you at the next video.